Today's AP Calculus review topic is limits. Limits is a topic that we cover at the very beginning of the school year, so definitely something we want to refresh as we're getting ready for the AP exam. The big idea on the front page says a limit exists if a function arrives at one y value. It doesn't matter what the value of the function is at that specific x value. It only matters that the function is arriving at one particular value for y. Consider the limit as x approaches 3 of the function f of x for each graph shown here. So the first graph has a hole at 3, so it's not defined at 3, but it still would have a limit. That limit as x approaches 3 for this function f of x would equal 5 because the function approaches 5 on the left and right side of the graph. For the second one, the limit as x approaches 3 of f of x does not exist because the function is approaching 5 from the left side, but it's approaching 2 from the right side of the graph. So since it has a different left-sided and right-sided limit, overall that limit as x approaches 3 does not exist. The limit as x approaches 3 of f of x for the third graph shown is equal to 4. This function is approaching 4 from both the left and the right side of the graph. So the left and right hand limits match, and it does have a limit there. You might recall that a sharp corner or cusp on a graph is a place where it does not have a derivative. It's not differentiable there. But for limits, it is fine as long as it's going toward the same number on both sides. Now the fourth graph here is approaching negative infinity, on the left side, and positive infinity on the right side. Even if they were, both going to the same infinity, the limit as x approaches 3 of this function f of x does not exist. Infinity is not a particular value. It's more of an abstract concept, and it does not represent a particular value, single number. So the limit does not exist. So there's a little below about the notation of limits. The limit as x approaches c of f of x equals L means the limit of f of x as x approaches c equals L. So that's just interpreting the symbols. As x gets closer and closer to some number c, but does not actually equal c, the value of the function gets closer and closer and may equal some value L. It may or may not actually get to the limit. Like on example 3, it does reach that limit. On example 1, it does not. All right, now we're going to talk about specifically one-sided limits. So the notation for the first one, the limit as x approaches c from the left of the function f of x equals L, and the second one, the limit as x approaches c from the right of f of x equals L. So the negative means it's coming from the negative side of the graph. The positive means it's coming from the positive side of the graph toward whatever the given c or x value is on the x-axis. So we'll look at these one-sided limits. If you want to pause the video and give them a try yourself and then check, that would be a good thing to do. The first one, the limit as x approaches 1 from the left side of the graph on this given f of x is 2, because I can see on the left side the graph is going toward the y value 2. The limit as x approaches 1 from the right side of the function f is also 2, and so that means the overall limit as x approaches 1 of f of x is 2 because the left hand and the right hand limits match. Now the limit as x approaches the x value 2 from the left side is 1 because the y value that the graph is getting closer to and closer to is 1. The limit as x approaches 2 from the right side of the graph is 0. So we're looking for the y value that the graph is getting closer and closer to as we approach that specific x value 2 from the right-hand positive side of the graph. So the limit overall as x approaches 2 of the function f of x does not exist because the left and the right-hand limits are not the same. So a function is said to be continuous at x equals c if, first, f of c is a finite number. That means not infinite. So you actually have a defined numerical answer for the y value, the y coordinate, at a specific x or c value. Secondly, the limit as x approaches c of f of x exists. And third, the limit as x approaches c of that function f of x equals f of c. So there's a 3-part definition for continuity. That's on your note cards, and you need to be very familiar with that as you're preparing for the AP exam because you must show all 3 things in order to prove something is continuous. So here's an example. Given this piecewise defined function, f of x equals x squared plus 3 when x is less than or equal to 2, and f of x equals 3x plus 2 when x is greater than 2, is f of x continuous at x equals 2? Justify. So first I'm just going to go in order. F of 2 needs to be defined. So for this piecewise defined function, I use the first piece. That's the piece that includes the 2. So I would sub in 2 for x, 2 squared plus 3, so that's 7. Okay, so it satisfies the first condition. The second condition is that the limit as x approaches 2 of the function f of x must exist. How will the limit exist? Well, it has to be going to the same value on the left and the right. So I'm going to plug in 2 for the x in the other piece of the piecewise function to see if it is going toward that same value. 3 times 2 plus 2 would give me 6, 7, 8. So the limit does not exist. So it fails the second condition. There's no need to proceed, so we can answer no, f of x is not continuous. The next example says, given f of x equals negative x squared when x is less than 1, and ax plus b when x is greater than or equal to 1, determine the values of a and b that will make f of x continuous and differentiable. Okay, so if I want it to be continuous, I need it to be going toward the same value when I sub in 1s for the x's. So I would want my negative x squared to equal ax plus b, which means negative 1 squared would have to equal a times 1 plus b. So negative 1 would have to equal a plus b. Then if it's differentiable, I need it to be going toward the same derivative on both as well. So if I take the derivative of the first piece, that would be negative 2x. And if I take the derivative of the second piece, that would just be a. So I plug in 1 for my x here as well. Negative 2 times 1 would have to equal a. So that means negative 2 equals a. So now I have an a value. I can sub that into my other equation. Negative 1 equals negative 2 plus b. Add the 2 to both sides. So positive 2 and negative 1 will make 1 equal to b. So here's an a value and a b value that will cause my function f of x to be both continuous and differentiable. Of course, you could plug those back in and check it if you wanted to, but we have completed that at this time. Okay, and it does say, note, something important, differentiability implies continuity, but continuity does not imply differentiability. And that is because of that sharp corner piece. If a function is differentiable, it for sure is continuous. But just because it's continuous does not mean that it's differentiable. A sharp cusp on a graph would be an example of a continuous function that is not everywhere differentiable. Now, we're looking at limits as x approaches infinity. So the basic rules with this is we're looking at horizontal asymptotes. Essentially, those same rules that you learned for determining horizontal asymptotes can help you with this. But for the first one, the limit as x approaches infinity of 1 over x squared, if that x is going to infinity in the bottom, that's one tiny little minute constant, and it wouldn't even have to be a 1. It could even be a million. But over infinity, as that infinity gets bigger and bigger, the numerator means less and less, and so that limit does equal 0. Anytime the degree of the denominator is greater than the degree of the numerator, you have a limit of 0. The limit as x approaches infinity of x to the 5th over 7, so this is kind of the reverse, the degree of the numerator is greater than the denominator. That is going to do whatever the end behavior of the overall function does. So if you can picture your parent function x to the 5th, it looks a lot like x cubed. It goes up to infinity on the right side. So this, even if I divide it by 7, is still going to be approaching positive infinity, which means technically the limit does not exist. On a multiple choice question, either one of those answers could be present and either one would be the correct answer. However, they will not put both as answer choices on the same problem. Okay, and if it was free response, which it's not likely to be, this is much more of a multiple choice format kind of a problem. It would be more specific to say positive infinity, but that technically means the limit does not exist, and I don't think it would be marked. I think it would be marked correct with either answer. So then the limit as x approaches infinity of 2x to the 9th divided by 3x to the 9th. Notice the degree of the numerator and denominator is the same. That means there is a horizontal asymptote. The horizontal asymptote is equal to the ratio of the leading coefficients. So 2/3 is the limit there. So you might want to pause the video and try the remaining 4 problems and then check to see if you get them right. So the limit as x approaches infinity of 3 plus x divided by x to the 4th minus 3x plus 7. All we really care about here is the highest degree power on the numerator and the highest degree power on the denominator. So this is like the same thing as x over x to the 4th, which would simplify to 1 over x cubed. And so this limit as x approaches infinity of 1 over x cubed is the same thing as the first example, 0. Then the next one to the right, the limit as x approaches infinity of, let's see what our biggest power in the top is, x to the 5th, and on the bottom x squared. So if I were to put x to the 5th over x squared, that would simplify to x cubed, and that's going to follow the same right-hand end behavior there, so it's going to go to positive infinity. The next one, 4x to the 5th on top, 9x to the 5th on the bottom. Same degree, a numerator and denominator, so the ratio of the leading coefficients would be the limit. On the last one, we have the greatest degree of x cubed in the numerator and the greatest degree for the denominator. Now, this is not a polynomial. This is an exponential minus a polynomial. Exponentials grow more than polynomials. So, and you just have to know that from a good understanding of all of your parent functions you've learned to this point. The e to the x is going to carry more weight than any other term in this particular rational function. So this would be comparable to that first one we looked at, where the degree of the bottom is greater than the degree of the top, because an exponential is going to make that grow way faster than the numerator. So we're looking at relative growth rates. This is called comparing relative growth rates. If the growth on the bottom is more than the growth on the top, then that is going to have a limit of 0. Okay, the next one. Horizontal asymptotes are described with limits going to negative and positive infinity. So y equals the limit as x approaches infinity of f of x is the equation of the horizontal asymptote going to the right if it exists, and y equals the limit as x approaches negative infinity of f of x is the equation of the horizontal asymptote going to the left if it exists. So we kind of briefly mentioned that already. Next we have the all-important definition of the derivative. F prime of x equals the limit as h approaches 0 of f of x plus h minus f of x all divided by h. So that's found basically by if I start with a point on my graph at any given x value, y value f of x, which f of x means the same thing as y. And then I just move a certain distance over along the curve. How far is not so important. You can just say it's h to the side. You have x plus h because you've just scooted over h, whatever. It's kind of a random value. And then f of x plus h. For the y value there, plugging x plus h in for x into the f function instead of just x. And so to find that slope, which is essentially what you're doing when you find a derivative, you do use the slope formula, which would be y2 minus y1 divided by x2 minus x1. So if I take the numerator of my slope formula, that's shown over here, f of x plus h minus f of x, and then the denominator of the slope function would be x plus h minus x. So the x's go away and you're just dividing by h. Now, as h approaches 0, so as these points get closer and closer together and I look at the limit of that slope, that's how I get the derivative. Definitely know that definition. So, let f be a function defined by f of x equals the sine of x plus 4 when x is less than or equal to 0, and f of x equals 4 minus x squared when x is greater than 0. A, show that f is continuous at x equals 0, and B, for x not equal to 0, express f prime of x as a piecewise defined function and find the value for which f prime of x is equal to negative 5. Okay, lots of work to do here. We're going to start by doing the definition of continuity. So first part of that is that I need to evaluate f of 0. So that's going to put me on the first piece. Sine of 0 plus 4. So the sine of 0 is the y-coordinate on the unit circle at the angle 0. So that's going to be 0 plus 4 equals 4. Now I need to find the limit as x approaches 0 of f of x. So I'm going to plug 0 in to the other piece to see if it's going to the same value. 4 minus 0 squared does also equal 4, so that means the overall limit of the function is equal to 4. And now I can see that f of 0 equals the limit as x approaches 0 of f of x. So there's your 3 parts to your definition of continuity. So it did say show that the function is continuous. It didn't ask me is the function continuous, so this satisfies that answer for part A. Part B. Express f prime of x as a piecewise defined function. Alright, so f prime of x is going to equal the derivative of the first piece. So the derivative of the sine is the cosine, and the derivative of plus 4 is 0. So we're going to be on that when we have x values less than or equal to 0. Then the derivative of the second piece, the derivative of 4 is 0. And then we have negative 2x to the first power when x is greater than 0. So there's the piecewise defined derivative. Now I need to find the value for which f prime of x equals negative 5. Well, I would be thinking set either piece equal to -5 and solve for x. But look at that first piece. Cosine of x, is the cosine ever equal to -5? Think about the range of the cosine function. It only goes up as high as 1 and down as low as -1 and stays yo-yoing in between those values. So it's never going to equal -5. So we're just going to set the second piece equal to -5. -2x equals -5. If I divide by -2 on both sides, then x would equal positive 5/2, or you could do a decimal, 2.5 if you wanted. So that's the value for which the first derivative equals -5. All right, next it says, explain in your own words what is meant by the equation, the limit as x approaches 2 of f of x equals 5. So you might want to pause and attempt to do that on your own, your words instead of mine. So if I were going to do that, I would say, as my function gets closer and closer to the x value of 2, the y value gets closer and closer to 5. That's in my own words, not technical math lingo. Is it possible for this statement to be true, and yet f of 2 equals 3? Explain. Yes, it is possible. You could have a function, a really boring function, that was like a line at y equals 5, except for when x is 2, there could be a hole. Pretend like that's not filled in there. And then 2 units down is a point filled in at 3. So there, the limit as x is approaching 2 from both the left and right sides is 5. However, the actual function f of 2 equals 3. Okay, the limit as h approaches 0 of f of 3 plus h minus f of 3 divided by h equals -2. Which of the following are true? So I want you to look, anytime you see something like this, I want you to write out your limit definition of the derivative. The limit as h approaches 0 of f of x plus h minus f of x, all divided by h, equals whatever value, -2. Okay, this tells me that I have been given a derivative of a function with 3 plugged in. 3 plugged in for the x. And it does exist. So if the derivative exists, then yes, the function's continuous at x equals 3. Yes, it is differentiable at 3. The derivative of f is continuous at x equals 3. Well, by the definition of continuity, the limit of that derivative would have to exist from both sides and be equal to the value. I really only know about what's going on at this derivative at the x value 3. I don't know what's going on just beyond 3, to the left of 3. Maybe there's a sharp cusp right next to it. I don't know. So that one I really don't have enough information to discuss, because I would probably need more than just a single point on the derivative. That just tells me the first condition for continuity, f of x has to exist, be defined, f of whatever value c or whatever is defined, and not infinite. That for sure is true. But the second two conditions for continuity, I don't really have enough information to make that determination. It doesn't mean that it's false. It just means I don't have enough information to guarantee that it's always a true statement. Okay, and find k so that f will be continuous at x equals 2, given f of x equals kx squared when x is less than or equal to 2, and f of x equals 2x plus k when x is greater than 2. Okay, if it's going to be continuous at x equals 2, then both of these pieces have to be equal to each other when x is 2. So I'm going to say k times 2 squared must equal 2 times 2 plus k. So this is 4k equals 4 plus k. Subtract k from both sides. So 3k equals 4, and then divide by 3k equals 4/3. So there's the k value that makes the function continuous. All right, you can finish out the problems. Answers are included, so you can check as you go. Good luck. Have a great day.